Probably 7:30, 8 o'clock in the morning tomorrow. Yeah, weird. It is because normally you're not supposed to know, right? Like it just happens. But C-section, yeah. Because my son was a C-section, so apparently this one has to be too. Some medical reason. Yeah.
I was a C-section. My mom just had all the other 6 without C-section.
Without or with? Without, okay. I don't know if it's some new policy or just this hospital's policy, but...
Well, like, they told my mom that, like, they would probably have to do a C-section with, like, the second one, and she was like, no, I'll be all right.
Okay. Well, she had the option. That's it. Well, see, the thing is, I don't mind. I'm not, or at least I don't think I'm going to mind having another C-section because I recovered very well from my first one. So I'm okay with that. I'm just hoping this one goes as well as the first one and not the other way, like a complete 180. But we'll find out. So when I am able to, I'll make sure I email him some pictures so he can share. Okay? All right, I think we left off on page 110. Last time we were together, we were looking at whether these sequences converged or diverged. And some of them were kind of simple. We looked at growth rates. Other ones were simple because we could look at terms. Some of them start to get a little bit more involved, and that's when maybe using a calculator might help us. So we're going to take or revisit K and L and see how using a calculator can help us with those. K is a little tricky because if you were to think going very deep into this sequence, like for instance, if you were to plug in infinity for n, like a really, really deep number, what is 1 over infinity? 0. 1 plus 0 is 1. And if you were to raise 1 to the infinity power, you would get 1. So you would think this would converge to 1, right? You would be mistaken, and we're going to see why on the calculator. L is a little tricky too, because when we talked about growth rates, we know a factorial grows slower than an n to the n or an x to an x function. So this would be something small over something large, which would eventually go to 0, right? So you might think converges to 0. But the fact that the 2 is included in the factorial function changes it. So we're going to utilize the calculator to see how that affects it and why it diverges. Okay? So in your calculator, I want you to type in this sequence into the y equals, just using x's instead of n's. And we're going to utilize the table command to help us see if this is going to converge or diverge. So table is listed in blue right above graph, so you got to hit the blue button first. Now my question to you is, if you were to hit this delete button next to the arrow keys, would it get rid of those values, or do they stay there? They stay there. Okay, so if they do go away, that's great. If they stay there, I want you to try this. The table set option is right above the window button, and I want you to change the independent option to ask. Okay, so what that's doing is changing the x values. Instead of the calculator automatically choosing them for you, if you set it to ask, you are telling the calculator what you want to plug in, instead of it choosing it. So that's the only thing I really want you to change. So if you go back to that table, I think it should be blank at this point, right? So what we're going to do is plug in some values for x that are signifying very deep terms into this sequence. For instance, if we plug in 100, that would represent the 100th term. If we plug in 1,000, that would represent the 1,000th term. Maybe you can plug in 10,000. Maybe you can plug in 100,000. Okay, you could keep going, but the idea is as we go deeper into the sequence, do we converge or diverge? So we said we would think this would converge to 1, like if we tried to plug in infinity, but clearly that's not the case here. Can you tell that we're converging based off those y values? Aren't we getting closer and closer to something? The question is, what are we getting closer and closer to? Do you recognize that decimal at all? Is my better question, I guess. It's E, right? Isn't E 2.718 yada 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 yada? Something, something, something. Okay, so this one actually converges to E. All right, so some of these can be misleading. Like we said, if we tried to plug in infinity, we would think it'd be 1. But if you have a calculator with you handy, you can always double check it, maybe using that table option. Okay? Yeah, sure.
Whenever I put in like 15 zeros,
Yeah?
it just says 1.
Not this again, really? Starts when you put in 14 zeros. All right, so I think this is another instance where I can't explain why that's doing it. Okay, we've seen that before, right? Where the calculator gives us a value that just doesn't make sense. I have yet to determine why that's the case. Okay, and I apologize if that's not a really good answer, but that's all I have at this point. Okay. All right, let's go ahead and check out the letter L. So we'll go back to the y equals. We'll clear it out. We need 2x, and then the factorial button on your calculator. If you hit math and go over to probability, okay, the last option on the right, the exclamation point is number 4. And then we're going to divide by x to the x. All right, so you can bring up your table again. Notice how it has the previous x values you already stored in there, so maybe that might be nice. All of these errors are just signifying that the number is too big. I mean, you could clear out all those x's if you want to and start off small, like 5, and then 6, maybe do 10, maybe do 100, and then you get that error. But notice how your number is getting drastically larger. Like that E8 is signifying scientific notation. Then you have to move the decimal 8 spots. So it looks like we're not really converging or getting closer to a number. We're just getting increasingly larger, aka diverging. Okay, if that 2 wasn't there, it would converge to 0 based off of the growth rates. But that 2 is being included in the factorial, which changes it. Okay, so calculator is going to be very handy, and we're going to utilize that a little bit more today, actually, in a little bit. What I want to do is practice a little bit more rule writing, because we're going to be doing this quite a bit in this section. So let's just go ahead and take a look at these first few examples. Remember, you can treat this as your first term, your second, your third, and your fourth. So we got to think of some rule. If we were to plug in 1, we would get 3. If we plug in 2, we get 8. Plug in 3, we get 13. Maybe you can find a pattern between those to help you out. Yeah. Say it again. 5n minus 2. Okay, so we'll label this as a sub n. Okay, whatever term you want, you can plug in that number and it'll give you that term. I like it. Is this 5 significant somehow? It's the difference between them. Yep. Okay, so notice how you add 5 each time. Do you think this sequence converges or diverges? Diverges, right? If we keep Adding 5 each time, we're not really going to get closer and closer to something. So that one would diverge. So this is a sequence that's called arithmetic. Okay, it looks like arithmetic, but it's pronounced arithmetic. And some things to look for these arithmetic sequences or series is a common difference, like that 5 we listed. And something else that's neat is if you can determine a common difference, the rule that you write is going to be in a linear format. You notice how this kind of looks like mx plus b is 5n minus 2. So you're going to have some type of linear rule. So those are two things to kind of look out for if you're going to write a rule. Is there a common difference? And if there is, it's going to be a linear rule. That common difference is most likely going to be the multiplier, okay, on that n value. What about the next one? Can we find a common difference or something that we're doing between them? Can we write a rule for part B? If you plug in 1, you get 5. If you plug in 2, you get negative 15. Yeah.
Multiplying by negative 3 in the previous one.
Okay, so we're multiplying by negative 3. So maybe that's something to look for. We'll label that as a common multiple instead of a common difference like before. So that negative 3 is probably important. That should be in our rule somewhere. Yeah. To the n minus 1?
No, times a subscript n minus 1.
So you want to do a recursive one, like something that deals with the previous one. We're going to try that for actually this sequence here. Okay, so recursive isn't bad, but I want to try to write one explicitly. Like if you plug in 1, this is what you get. If you plug in 2, this is what you get. Recursive isn't bad, because technically that is still a rule. But the explicit ones are a little bit easier. Because if you plug in a number, you get your answer. You don't have to worry about a previous one. This one's a little tricky. Let's see, the common multiple is negative 3, but aren't all of these also divisible by 5 somehow? So maybe 5 is important to use? Alright, let's check this out. We'll talk about it. Okay, we're going to have a multiplier of 5 out front. And what about if we put some power on this negative 3? So 5 times negative 3 to a power. Now if I plug in 1 here, I would have negative 3 to the first, which is negative 3, times 5 would be negative 15. But that's my second term. If I plug in 1, I should get my first term. Yeah.
So it's
N minus 1. Right. You might have something extra that you need in that power position. This is what's referred to as a geometric series or sequence. That's when you have a common multiple. And these rules are going to look like exponential functions. Okay, or an exponential rule. So you're going to have that common multiple to a power this time. We're going to talk about geometric sequences and series probably tomorrow. Okay? So some things to look for. Is there a common difference? Most likely arithmetic. Is there a common multiple? Most likely geometric. And then we can utilize the type of rule to help us write out the rule itself. Let's go ahead and check out C. Is there a common difference we can identify? Is there a common multiple we can identify? If neither one of those are the case, then it's not going to necessarily be linear or exponential. It could be any other rule that's necessary. Can we find some type of pattern between all those numbers? If you plug in 1, you get 1. You plug in 2, you get 4. Plug in 3, you get 9. Yeah? N squared, right? Good. We didn't do converging or diverging. What about part B? Would this sequence converge or diverge? Are we getting closer and closer and closer to something? No. So automatically that would be diverging. What about the next one? Part C, converge or diverge? Probably diverge as well. All right, let's check out D. Can you identify a common difference? Can you identify a common multiple? If you plug in 1, you get 4. You plug in 2, you get 10. Tripping us up a bit? Maybe? Can we make a similar sequence, perhaps, and then relate it back to this one? What if I did this? Does that help? What do you see, Eric? Yeah? Alright, so the rule for this sequence is 3 to the n, okay, 3 to whatever power, but this isn't the rule, or this isn't the sequence in question, this one is. So what do you have to do to this sequence to get that one? You'd simply have to add 1. Okay, so maybe you can manipulate your sequence a little bit, okay, making sure that you're constant as you make your changes. Like notice how we subtracted 1 each time? Well, you can't just make up numbers without it being consistent all the way through. So maybe you can manipulate it a little bit to help you write your rule. All right, converging or diverging? Probably diverges. We're not really getting close to anything. Let's try the next one. You plug in 1, you get 2 over 1. You plug in 2, you get 3 over 3. Plug in 3, you get 4 over 5. Notice how all these are going to be fractions, right? So maybe we can figure out a rule for the top numbers over a rule for the bottom. Like pick it apart piece by piece. Wait, you see it, Caitlin? Yeah. N plus 1, yep. If I plug in 1, I get 2, plug in 2, get 3, plug in 3, get 4, checks out. Rule for the bottom ones. Yeah. 2n minus 1, good. That's kind of the rule for all the odd numbers. 2n minus 1. Good. Converging or diverging? Can you tell based off the terms? Can you tell based off the rule now that you have one? Yeah? It is. Yep. How'd you know 1/2? Yep. The 1 divided by 2, we have the same growth rate. They're both an n to the first power. Good. And what about our last one? We can probably assume the natural log is going to be a part of it somehow, right? The question is, it's the natural log of what? If you plug in 1, you get 1. Plug in 2, you get 2. Plug in 3, you get 4. Yeah? 2 to the n minus 1 power, is that what you said? 2 times a. You're going to do a recursive one again. Okay. So 2 times like that. That would work for recursive. Yes. Okay. So a recursive rule could look like that. 2 times, well, wait a minute. If you say the previous term, you're talking about the whole term itself. E? Oh, that would get rid of it. Okay, to the a n minus 1. That would get rid of it. Yep. Okay, so you could leave it like that for I'm going to label this as recursive. That's if you want to list it in terms of a previous term. Okay, but what about if we wanted, like if we plug in 1, we get this. If we plug in 2, we get this. It's a little bit more straightforward. I like the 2. What can we do to 2 to get 1? What can we do to 2 to get 2? What can we do to 2 to get 4? 2 to get 8? Yeah? And minus 1 power. Good. If you plug in 1, you'll have 2 to the 0 power, which is 1. Plug in 2, 2 to the first, which would be 2. Plug in 3, 3 squared would be 4. Check it out. Alright, so you can write it both ways. There are other ways to write these as recursive as well, but you're going to see most of the time we're going to be dealing with these more straightforward rules. Okay, but I'm not saying it's a bad thing to know how to do recursive. That's just something extra you're able to identify. Converging or diverging? We getting closer and closer to something, or not? Converging to what? I think we're going to diverge. Okay, notice how the inside the log, the number's just getting larger and larger and larger and larger. But when you take the natural log of something, okay, that's just another value itself. So these are going to get larger in turn after you take the natural log of them. So that one's going to diverge. Looks good. So Autumn mentioned how you guys kind of have a big test today, perhaps. Is it just you, or? I don't know. Anybody have a...
I think it's just me.
Any government or history test today? You already had it? Just you? Okay. I'm going to keep going, but if you want to stop, that's okay. It's up to you. Okay? Alright, so up to this point, we've just been looking at sequences. Have you guys noticed how all of these have been separated by commas, right? We're now going to transition into series. Okay, what if we were to add all these terms together? So we're going to take a look at that sigma notation a little bit more. Let's take a look at the two examples at the bottom here. We're going to take a look at something called partial sums. So we're going to add up all the terms, but only to a certain point. So for instance, let's maybe look at a sub n first. If I wanted to find the first partial sum, I would denote that as s sub 1. Okay, it's normally s sub a little number. So that just means I want to take the first term, because that's basically all I'm going to have. If you plug in 1 for n, what would your first term be? You'd have 1, right? So your first partial sum is 1. Let's try the second partial sum. So you're going to find the first and the second term and add those ones together. So if you plug in 1, you get 1. If you plug in 2, you get a half. And we'll add those together to get 1.5, aka 3 over 2. The third partial sum is if you were to find the first 3 terms and add those together. So we would need 1 plus a half plus a third. Let's see, common denominator would be 6. We would have 11 over 6. And 11 over 6 as a decimal, 1.83 repeating, I think. Let's go ahead and try the fourth one. So we would need 1 plus a half plus a third plus a fourth. Common denominator is 12. We would get 25 over 12, which as a decimal, 2.083 repeating. Alright, what if I asked you for the 999th partial sum? Would you guys feel like doing that? No, not at all. Okay, so let's go ahead and utilize our calculator for that one. So we're basically going to utilize the sigma command on our calculator. Remember how to find that on here, which buttons we press? We go to math. Option 8 is derivative. Option 9 is integral. Option 0 is summation. So we'll let our x values start with 1, and we want to add everything up to the 999th term. So we'll let that be the upper bound, and then we'll write in our rule 1 divided by x. $7.484. Can we get that? Okay. Alright, so notice how we started off pretty small with the partial sums when we were adding things together, but eventually we were traveling deeper into this series and we got 7.484. Based off of our partial sums, would you say this series, okay, of 1 over n, does it converge or diverge? Like if we were to start with an n value of 1 and go off towards infinity and add everything up, are we getting closer and closer to something, or are we just continuing to increase without bound? You have an idea, Caitlin? It's just going to keep going on and on. It's not going on and on and on very quickly, right? Okay, but it is going to keep going on and on and on. You can check higher partial sums. Okay, on your calculator, if you wanted to plug in 100,000 there, you could. It might take some time for the calculator to calculate all of it. Okay, it's going to use some think time. But I would definitely guess it would be higher than 7.484. So it looks like that this series diverges. Have we seen something like that before? What does this notation kind of resemble? Could we use a different calculus symbol instead of summation and it would look like something? Huh? An antiderivative, okay, meaning an integral. If I were to change the sigma into an integral symbol, wouldn't it be integral of 1 to infinity of 1 over n? Right? How do we already know that one diverges? Do you remember what it's called? Maybe 1 over x would be better? P-series. Yep. So there's a nice little connection there. Okay, we'll take a look at that later in this section too. Let's try the next one. Okay, this time our different rule is 1 over n squared. So our first partial sum, if we plugged in 1, would be 1. Our second partial sum, we'd have to plug in 1 and 2 and add them together. So that would be 5/4, but as a decimal you can write 1.25. Your third partial sum, you got to add the first 3 together. Let's see, as a decimal, 1.361, I think, repeating. Maybe we'll just jump to the chase. We'll go straight to the 999th. What'd you guys get? 1.64. Sounds about right. Okay. So, do you think converges or diverges? If you wanted to check more like higher powered or higher termed ones, you could. But maybe this might be enough for us. Do you think like we're getting closer and closer to something, or are we going off without bound? Would you guys think we're converging? Okay, so this one is converging. Maybe we don't know to exactly what, but at least we know we're converging. Okay, and doesn't this summation kind of look like it's related integral? Right? If we did the integral of 1 to infinity of 1 over n squared, don't we know that converges by p-series? Right? Our power is bigger than 1. Do you remember what this would converge to, the p-series integral? Remember our little shortcut? Say it again. How'd you get 1/2?
1 over 2 minus 1.
So what's 1 over 2 minus 1? It'd be 1, right? Okay. So what's a little tricky here, notice how there is a connection, okay? If the integral converges, notice how the series converges. If the integral diverges, the series diverges. But if the integral converges to a number, that's not necessarily what the series converges to, right? This integral converges to 1, but clearly the series is not converging to 1. You're not getting closer and closer to 1. So there is a connection, but there's not an exact connection. We're going to discuss that a little bit later in this section too. Okay? Let's take a look at a few more of these partial sums. Okay? So given this series, they give us the rule in a few terms. We're going to find the first 10 sums. So maybe you guys can utilize your calculator for this. If you start with the first term, that's just a half. If you add the first 2 terms together, you get 1.125. If you add the first 3 terms together, all right, you guys keep going. Find the first 10 partial sums. I'll write them up here. You guys check, and if there's a discrepancy, you let me know, okay? Those numbers check out? Okay, so as we continue to get deeper and deeper into this series, okay, adding everything together, does it look like we're converging or diverging? We're getting closer to something or infinitely larger or smaller? Probably say converging. Can we determine to what? What are we getting closer and closer or closer to? Does it seem like something? To 3, right? Looks like it. Okay, so this one is converging to 3. Now there is something I want to kind of point out here. Kind of the difference between these two notations. If we were to look at the rule itself, like the 3 over 2 to the n, if you were to go deep into that rule, okay, like plugging in infinity, you would have 3 over something huge, which is approaching what? 0, right? However, if you look at this summation of the rule, if you were to add all of the terms together, we said we are getting closer to 3, right? So there's a difference between these symbols. One of them is representing a limit, the other one is representing a summation. Whenever you're analyzing a limit, you're looking at the terms, okay, kind of the sequence. So if we were to put commas in between all of these, the sequence would approach 0, right? The individual terms get closer and closer and closer to 0. But the fact that they're now addition symbols instead of commas means we're working with a summation. So the sum is approaching 3. Do you see the difference between the two? Even though the terms are getting smaller and smaller and smaller, closer and closer and closer to 0, if you were to add all them up, you'd be getting closer and closer and closer to 3. Okay, we need to understand the difference. So the terms, we're analyzing each individual number, whereas the summation, we're analyzing the addition of everything together. Do we see the difference between the two? I don't want you to get too confused between the 0 and the 3. Okay, they mean two completely different things. This is what the terms are doing versus what the sum is doing. All right, we'll stop there for today and take a look at a similar example for kind of practice tomorrow. Okay?